I'm Lucian Fogoros. I'm the co-founder of IoT World, and I'd like to thank you, the 770 plus people from 80 countries, for joining us. I'd like to take this opportunity to thank the sponsor of this session, Hitachi Ventura, for making this possible. At this time, I'd like to introduce our moderator for today, Dan Isaacs, the CTO of Digital Twin. Dan, the floor is yours.
Well, thank you, Lucian, and thanks for the opportunity to moderate this esteemed panel. My name is Dan Isaacs. I am the CTO for the Digital Twin Consortium. And just a quick overview in terms of the Digital Twin Consortium, a little bit of an introduction. We were formed a little over 2 years ago. And as you can see, we're really focused on not just driving the awareness of digital twins, but also really accelerating and driving the adoption of digital twins. And from the next slide, as you can see, we're part of a larger umbrella, which is called the Object Management Group. And you can see here, we have 7 different consortiums or communities of like-minded interest. Our most recent is what we call our responsible compute, looking at all the different aspects relative to environmental, societal, governance, ESG, and sustainability. Prior to that, our other one is Augmented Reality Enterprise Alliance. And that has I believe, over 70 members now, looking at it from the standpoint of how does augmented reality impact in these different areas, and understanding that with the likes of Siemens, Medtronics, Lenovo, many others as part of that alliance. And what's unique is that through this object management group, with these communities of like interest, we're able to now have liaisons between them and collaborate and have cross collaboration in those different areas. So little of my background, I came from software side, hardware side systems, so technologist at heart, and represented my previous company to the Industrial Internet Consortium, the Industry IoT Consortium, there for 6 years, and worked on multiple areas in terms of developing technologies, test beds, from the both programmable logic side as well as programmable SOCs, and really driving specific test beds forward, including using machine learning for predictive maintenance and smart factories. The Digital Twin Consortium, as I said, was formed a little over 2 years ago, and 2 weeks into its formation, I was asked to come in and provide that technical direction for the consortium. And the consortium was founded, next slide, please. The consortium was founded by, This consortium was founded by 4 original founders. It was Dell, it was Microsoft, it was Ansys, as well as Lend-Lease. And the interesting aspect is the chair of our steering committee is the CEO for digital transformation at Lend-Lease. But prior to that, he was the CEO for GE Digital, and was able to look and see and understand all the values and drive the opportunities for using digital twins to provide the productivity improvements, the efficiencies, all the values that are recognized by using a digital twin. So we have over 10 working groups right now, represented through different vertical segments, such as manufacturing, aerospace and defense, infrastructure, our mobility and transportation, healthcare and life science, natural resources. We have smart agriculture and food and beverage. We have many different verticals represented throughout the Digital Twin Consortium, which we can leverage this relationship throughout the overall umbrella of Object Management Group. And it's really with a great pleasure. We started with 50 members, and now we have closing on 200 members. So you can see our complete list. If you haven't heard about the Digital Twin Consortium, I highly encourage you to go to our website, digitaltwinconsortium.org, take a look and learn about all these opportunities through collaboration in our membership. We also have stood up an open source collaboration community as well. So really great opportunity here. Thank you again for being able to moderate this, this esteemed panel. And with that, we're going to jump right into it. So we'll introduce our first speaker. Matthew Klusek is the market research analyst for IoT analytics, and wanted to be able to really share his depth of insight in terms of trends and challenges that are being faced, organizations are faced with, and including facts like the macro level changes, challenges, and trends such as supply chain issues, and how digital twin technology and AI can help to manage these disruptions along with other technologies and trends going on. So Matthew, please.
Thank you. Hello, everybody. Thanks for joining. So yes, we will start by picturing the broad macro environment, and then we will deep dive into technologies enabling to edge against this worker knowledge gap. So if we can go to the next slide, please. So we are IoT Analytics. We are a market research company focusing on IoT and industrial software. We make market reports, dashboards with data, and also bespoke services. So all of the slides that you are going to see now in these presentations are highlights from our reports that we published and also research that we are doing now. Let's move on, please. So first, we will start with some overarching macro trends. So the first trend I would like to talk about is quite an interesting one. It is that now the overall business and macro level picture is much more unstable than we had 2 years ago. So what we do is that every quarter, we look at earnings call for about 3,000 companies which are related to technology and software and operating globally. We look at what CEOs, CTOs, and high-level, C-level decision makers are saying. And we're looking at the trends, the keywords. One of the key takeaway here from this slide, where we can see how many times the keyword shortages in supply chain are mentioned, is that shortages in supply chains are quite a concern for most of the companies, about 60% of the earnings we looked at in Q4 2021. And it's quite a raising concern, so more than 5 times that what we had last year. Now, let's move on to the next slide, please. If we zoom out and we compare that to all of the data that we have historically, with this index, that is the supply chain pressure index that is coming from the Fed in the US, we can see on the right of the chart that the supply chain pressures are easing, but we are still quite far off for what we had before. So if we compare to other events like in 2008, the financial crisis, or 9/11, we are still quite far off, but we're still improving. Now, let's go to the next slide, please. Coming to our topic about digital twin and AI and analytics. What's quite interesting in this analysis that we do when we look at what CEOs talk about and high-level decision makers is that when they mention supply chain issues, disruptions, they also talk about AI analytics or digital twin. And when we deep dive in this data, we realize that they mention those keywords and topics as ways and strategies to edge against those disruptions. So that means that they are looking at how could they make their process better, how could they gain more efficiencies, and they usually look at AI and digital twin. So now let's move on. So let's talk now about labor shortage and worker knowledge gap. Here, it's quite an interesting slide. What we look at here is the number of job vacancies that are posted online globally from all kinds of companies. The first takeaway is that in March 2022, we had more than 1 million AI and data-related job vacancies online. So that means that high-level decision makers, they see that their business and their environment is much more disrupted than before, clearly more than 5 times more disrupted than what we saw before. They are searching for new tools to make it better, to find ways to edge against disruptions. And they're also searching for people who have a lot of skills in AI, digital twin, machine learning, data science, and analytics. So I must mention that this trend now has been decreasing because of inflation or other macro level environments since the last few months. But overall, we are still increasing in more search for this kind of skills. Now let's move on to the next slide, please. So let's deep dive now in the technology that is enabling to bridge these gaps. So the first trend I would like to talk about is that software, and by software I mean industrial software, is becoming more flexible and easier to consume. So when we look on the left of this chart, we can see the picture that we had on the industrial software market in the early 2000s. By that, I mean that if you were industrial manufacturer working for your specific use case and wanted to go into purchasing a software to digitize your operation, you had the choice between some quite rigid, high-level bundle of one ERP software, one CRM, or one MES software. The data the data exchange was quite limited, honestly. There was not so much exchange, and it was quite rigid. You needed to subscribe for 1 or 2 years. Then 10 years later, we started to have some moves, some data exchange between the software kind of silos, but still quite rigid. Now, the interesting thing that we see now since the early 2020s is that thanks to technologies such as cloud computing or go-to-market strategies, such as offering software as a service with SAS, now software is breaking down into small capabilities and then bundled in some cloud hybrid edge platforms. So by that, I mean, we're looking on the third picture from the right, from the left. I mean that if you are now an industrial manufacturer, you're looking into digitizing your operations, you can go ahead, go into an ERP, select the specific sub capability that you're searching for, bundle that with something else from a supply chain software or CAD software, and then purchase it and pay it as you go with software as a service. I know that's the direction where we are going, more flexible software to cloud or edge marketplaces. So now let's move into the next slide, please. That brings us to this point. Software is becoming much more important in the manufacturing environment. So much that here we see the total industrial software market compared to the OT market. And for the first time in 2022, industrial software was more important than operational technology, than OT. And thanks to a lot more value added through AI and new capabilities for the end users, we forecast that the industrial software market is going to be twice as big as the OT market by 2027. Now, let's move on to the next slide, please. So now let's talk more about AI. On the left, you can see the Google Trend Analytics from machine learning. So machine learning being the most popular form of AI, just sitting right between general AI and deep learning. And it's quite exponential. When we see from 2019, much more people are interested into AI, searching to understand what it is or to clearly implement it into new use cases. That brings us to the next slide. That brings us to $100 plus billion opportunity in market by 2026. So we forecast that by 2026, the industrial AI market, so any kind of software that will have AI on top or bespoke AI capabilities, will be accounting for about 100 billion plus market by 2026 with a quite high CAGR, so about 35% CAGR from 2020 to 2026. The best adopter now that we see in the industrial setting would be discrete manufacturing, especially in East Asia and Japan, yes. And also the best use case would be looking into predictive maintenance, quality inspection, or optimizing general processes. Let's move on to the next trend, please. Yes, so that's about it. Thanks a lot for your attention. If you want more detail and if you want more data about these slides, please feel free to reach out to us on our website. Thank you.
Excellent. Thank you, Matt. Lots of really great information, insight. I'm sure there's going to be already seeing questions regarding some of the content. So we'll follow that up in our Q&A session. But next we have both Stephen Garbrecht, Director of Product Marketing at Hitachi Vantara, as well as Fabio Terasaka, a Senior Product Manager at Hitachi Vantara. And they're going to basically be discussing their AI ML solution, including an overview of capabilities and solution offerings for intelligent data management. And this will be followed by both customer use cases and demonstration of the solution. So with that, I want to introduce Stephen, please.
Great, thanks, Dan. All right, well, thanks again for everyone attending this webinar. We'd like to talk a little bit about the solution that we have with the Mata Industrial Data Ops portfolio as part of Hitachi Vantara. And I think you might find it interesting and also a great addition to the kind of things that Matt talked about. So on the next slide, we've done a lot of research with companies out there as far as what they're looking for with regard to AI and ML activation in their organizations. And as you can imagine, AI and ML is something, as Matt said, is being used to counteract the exit of the trained workers in the workforce and new people coming into the industry. But the problem with AI and ML is it's very time intensive to organize and create applications and solutions that fit into this space. There's a lot of risk associated with it. In fact, about 70% of the time that it takes to create these analytic applications is just in aligning the data, organizing the information, setting up the use cases, collaborating between the IT organization and the OT organization to make things work, and so forth. These activities are also things that data scientists and data engineers hate to do. They'd rather spend more time on high value activities like actually creating the models and organizing and converting the data into useful information as part of that. So some of the capabilities that we've noticed are really required for a solution in this area include self-service. So being able to actually organize the data and browse it and leverage it without having to get a lot of people from the IT organization or the OT organization involved in actually gathering and assembling the data for your use. Also providing greater analytic readiness. So being able to convert the data and provide more context to it so it can be used by a broader set of individuals in the organization. There might be certain subject matter experts that really understand the data, being able to prep it more easily for the data scientist and the solution engineers to use it is very important. Also, providing the ability to have a faster starting point with some pre-built models that can be trained using your data that also are enriched and leveraged with the configuration of a digital twin that can represent your high value asset that you want to leverage within the solution, and providing just the base capabilities of security and integration as a platform to be able to apply to the solution in general. And then one of the most important things we've seen is a lot of IoT and analytic projects so far have been, some extent, individual pilots at individual sites and haven't really scaled across the enterprise. And when they've gone in, you choose a particular vendor or a use case. Typically, you're just looking at, what data integration can I use for that one application. And if you go to create another analytic solution or use another vendor, a lot of times you need to rebuild that whole capability, that whole data set and integration that you had before. So why not put it in once so you can use it for all of your analytic solutions? Help it to manage your data lake environment or your data hub environment with a standardized capability to browse data, leverage it, set up data pipelines, convert the data, and use a more of a professional approach in how you go after it so that it can really scale across your enterprise and multiple analytic use cases as part of that. So on the next slide, we provide this capability, in fact, with Hitachi. And we have our industrial data ops portfolio, which provides the value of being able to onboard both IT and OT data sources. We have connectors to over 150 proprietary OT systems like PLCs, control systems. But then we also have integration with IT systems and industrial databases like historians, MES systems, APM, ERP systems. We can also integrate with social media and customer relationship management systems, weather systems, and industry feeds coming from governments, for example, for safety alerts and things like that. All that can be combined and pulled in and leveraged. These can be managed as data pipelines where you can convert the data and clean it as it goes along, forward it to individual databases, either in your data lake or at the edge or in the cloud, and then coordinate the overall activities of those data movements so that they're constantly maintained and governed as part of that. Then you can further classify the data and organize it and add additional metadata to it to make it more useful for people even outside of the operations organization. So say people in your marketing department or sales department or your customer relationship management department now can understand this data even more thoroughly. Then we also provide an environment to be able to transform it and leverage the data models you would create inside of your data science activities to be able to train the models more efficiently, keep track of the results of those trainings, and also to more easily assemble them into useful applications with UIs and dashboards and alerts that can tell people what to do as part of that. So providing a better capability to connect everything together, respond faster, and develop these applications with less effort, to predict failure, and also to prescribe analytics to people to do things, and enable your overall applications enablement and your environment for developing and managing analytics across your operation. So with that, let me go ahead and turn it over on the next slide here to Fabio, talk a little bit about the capabilities we have in depth.
Thank you, Stephen. Good morning, good afternoon, everybody. I would like to talk a little bit about the digital twin and the solution architecture that we employ in Lumada, which is the platform that Stephen just described. So for that, let's start with the next slide that talks a little bit about the definitions of digital twin for us in Lumada. So the basic concept of the digital twin for us is that it represents a physical asset or a physical device in the digital world. So in this picture, you can see the physical device on the left-hand side and the digital representation of that device of that piece of equipment in the virtual world. So that is the basic notion of the digital twin as it exists in Lumada today. Right? One of the key characteristics for us when you create this digital twin is that it becomes a living entity. And what that means is that this living entity, it represents accurately what is the state of that asset in any given time and what are the functionalities associated with that asset. One of the key notions in order for you to do that is that you can both read information coming out of the digital twin in near real time, and Stephen talked about several types of information it can be associated with it. It can be maintenance records coming from relational data sources, it could be design documents, it could be OT information coming from sensors, but also, in some of the use cases that we have seen for digital twins, you may also need to trigger actions on the physical device based on what you're doing in the digital world. So the typical use cases, for example, if you calculate set points, if you calculate optimize operating conditions for the digital twin, based on it closely relating what the real world device or asset is doing in the real world, that you can then replicate those conditions in the real world once you have done simulations, optimizations virtually, right? The next characteristic that's very important for us when we're talking about digital twin is that it has to be scalable, it has to be customizable and resilient to failure. So one of the things that typically happens that we have seen in the past is that many of these projects involving digital twins, they're stuck in what we call the POC hell, right? So you go and you do one POC, but it's very difficult to scale beyond that one single, very narrow implementation. And we have heard from customers that some of the challenges that they have is, okay, we have proven the value in this small scale pilot or POC environment, but it becomes very uneconomical to deploy that at scale. So for us, in Hitachi, and I'm going to demonstrate that when we go to the demo, we have the means to scale this to hundreds and thousands and millions of devices, and to also customize these things. So every copy, every digital twin can be customized in its attributes and behavior. The next definition, the next attribute of the digital twin for us is that it has to be able to be grouped, split, it has to be able to be part of hierarchy, and all of the above, right? So just as an example of this use case, if you think of a manufacturing plant, if you think of a power transmission line, each of the assets that exist in those verticals, they don't just exist there in isolation. They're part of a broader context, right? And it's typically important for you to know what is the effect that any condition in one given piece of the network has on the overall system, right? So in order for you to do that, in order for you to simulate those kinds of scenarios, it's important that you're able to group those entities together so that you can evaluate those relationships. In some cases, you may have to split them apart in order to achieve certain use cases. And in many cases, these things will be part of a hierarchy. So if you think of a manufacturing plant, perhaps you're modeling the whole plant as the overarching hierarchy of digital twins, but then you can subdivide that plant into its parts, into its areas. In areas, we have the piece of equipment. Each piece of equipment has its subcomponents and so on. So our digital twin system allows you to do all those kinds of grouping, splitting, hierarchy, so that you can model those network effects and you can start understanding what are the ramifications, right, in the overall system. And last but not least, we already touched on this, but the digital twin for us is the vehicle, is the backbone that leads to all the data, right? This has to be a bidirectional communication by which you can both read information originated from the physical device itself, and in limited cases, when you want to send something back to the physical device, that capability should also be there. So we already talked about being able to read from sensors, being able to read from relational data sources, design data, project data, documents, photos, everything can be associated with digital twin. To illustrate that a little bit more clearly, let's go to the next slide. And this will highlight how we typically apply the digital twin in Lumada in a project or in an implementation. So this is how it typically works. It starts on the left-hand side with the asset. So that is a typical industrial asset that we deal with. And it will have several types of data associated with that asset. So we already talked about having near real-time sensors that measure things in the field, but it may also have other things which are relational in nature. It could be unstructured data, right? So the first step in the journey is to do the data ingestion through the edge in data ingestion component. But that's just a stepping stone to connect that data from the digital twins, from the assets to digital twin, which is the backbone in blue in the center of the picture. So the digital twin for us is what does the entire orchestration of workflows, data, calling the machine learning model, relaying the information to the visualizations, to the events, to notifications. So the digital twin in this case can be associated with one or more physics-based simulators. And the physics-based simulator is one essential component of the overall architecture, in the sense that it can closely simulate the physics and the conditions and the reactions that the real world device would have to certain parameters. So to be specific, we have had a use case where we were reading 10 or 12 pieces of sensor data. And in order for us to provide a more accurate prediction for the customer in terms of what was going to happen with that particular asset, we needed to simulate exactly and with high fidelity what that asset would do if you change certain parameters in the field. Not only that, but it's typically the case, especially in brownfield scenarios, where you may not have sensors installed for everything that you want to measure, right? So for those cases where it's either uneconomical or it's impractical for you to go and install sensors for those things in those high value assets, these physics-based simulators allow you to do what we call data enrichment. And the data enrichment is a process of calculating things which may be hard to measure or impossible to measure. An example could be torque, or you could have, for example, angular velocity. These kinds of things can be all simulated virtually, whereas in the real world, it would be very difficult to sensorize and to measure those things in near real time. So by enriching the data set and associating that with digital twin, we have seen in reality how they can make one or more machine learning models more accurate, because it is enriched with these things like torque, virtual sensors, and so on, right? So the physics-based simulator is an essential component for us in this architecture, and the digital twin, again, coordinates all the communication with those kinds of systems as well. So once the data is enriched by the physics-based simulator, the digital twin can also be the broker to interface with one or more machine learning models, right? So one of the things that we talked about is the ability to perform prediction, the ability to be ahead of the curve, right? So the digital twin in our hierarchy in Lumada, it allows you to train and deploy several machine learning models. In this particular case here in the picture, we're using an anomaly detection and prediction model, but it could be, for example, an image classification. It could be a schedule optimization. There's many types of models that you can apply to this platform. And the goal here is that, again, using an enriched data set, using the physics-based simulation, the high fidelity simulation, that those models will be more accurate because you're dealing with an enriched data set, right? So in this particular case, we're calling the anomaly detection prediction model every couple of minutes, and that produces an anomaly score, right? The inferencing results that we see here in the picture, and those inferencing results can then be fed into visualizations, events, and notifications, which complete the workflow, right, by providing the maintenance person, in this example, with the information that's required to optimize the asset that we started from on the left-hand side. So with that, I would like to do a live demonstration of how some of these pieces work in real time and in the real systems. So let me start sharing my screen here. And we'll start from the beginning. So we talked about connectivity, right? So one of the first steps in connectivity is reaching out to those industrial devices. And here we have one of the components of Lumada, which we call Edge Connect. And here you can very easily create the data routes and the data access to all types of data sources. In this particular case, you could connect to Rockwell, CAN-bus, Beckhoff. We also have others from Emerson, GE. So at this level of connectivity, what we're trying to do is to establish the digital twin, right? To have real access to the information coming from, real-time access to the information coming from the sensors, the OT devices there, right? So once this particular step is configured, and this is very easy through this wizard, all this information is then sent to the digital twin. And here I have created a sample hierarchy here in this other tab. So here we can see that we have several digital twin hierarchies created here. We have a grid type of asset here. You have a gas turbine site, right? And all these, they have also children and subcomponents as we described. So in this particular case, if I am interested, for example, in this gas turbine, I want to provide an outcome for this. I can click on that device, on that asset. Log me out here. Yes, so this is the asset, the high value industrial asset that we're providing an outcome for. And in this particular case, it's a gas turbine. Here you see some metadata associated with this digital twin, right? You can also see the data routes. The data routes is the access to the data, right? So we saw in the first component how we connect to the OT sources, and this is basically that module sending data to the digital twin right here. The other thing that we can do here, we can see what is the model, right? The machine learning model that's associated with this particular gas turbine. We have one model in this example, and this is an anomaly detection and prediction model that generates outcomes for that turbine. One of the things that we have here in Lumada as well is the ability to create what we call asset types. So the asset types, these are meta representations of a given asset. So we talked about the need to scale these things to thousands, hundreds of thousands, perhaps in some cases, millions of devices and assets. So the asset type allows you to model the asset at the general level and then create multiple instances, hundreds of thousands of instances that are identical in nature to this asset type. So this is basically you're creating an asset type that represents the gas turbine. You can model all the attributes here. And then if you have 10 of those here in the asset hierarchy, you can very easily create 10 cookie cutter versions of that asset type. But more than that, we also talked about the ability to customize the attributes and customize the behaviors of those individual instances. So when you're, for example, dealing with this one instance of that type, it's also possible, if you click here on the edit button, you can also come here and add specific properties in specific attributes, which are only applicable to this one digital twin, but not to the other ones that are of the same type. Right. So these are some of the ways how we can really scale, really provide that flexibility and customizability features for our clients. The other thing is that also here, you have all the API documentation readily available. So all the asset hierarchy, all the devices, all the sensors that we connected, they're easily managed through this REST API. And this makes it a very open system for you to interface with. And in case you want to build applications based on these capabilities, that's all immediately available and fully documented. But it doesn't end here. As we talked about, the digital twin is the backbone of this entire system, but it has to serve a purpose. And what is that purpose? So we talked about this gas turbine here. In this particular case, we had an anomaly detection and prediction model, but this is just one type of analytic outcome, one type of machine learning outcome that can be driven, right, based on the digital twin. We could also create, for example, another digital twin hierarchy here that simulates, for example, the South Texas grid, where you're simulating, you're modeling all the transmission towers here in this system. And this can be then used in an application. This can then be used in an application like this one. This is our Hitachi image-based inspection application. And what we have here is basically the entire grid modeled in the digital twin hierarchy that I just demonstrated. So if I want to know more about the modeling that's underneath this particular region, I can click here a couple of times, and then we will see that the grid will pop up here. Yeah, so this line here, this is the grid, and this is modeled based on the digital twin capabilities that we just demonstrated. So this is an application that can be built on top of the digital twin infrastructure, and this uses a slightly different machine learning model. In this case, we're not doing anomaly detection prediction. In this case, we're using a different model that does image classification. So the way how this workflow works is you have drones, automated drones that can go to these transmission towers, and they can take pictures of those towers with the goal of identifying potential failures based on those pictures. So what you do is you can model all these assets on the digital twin hierarchy. You can use the drone to capture the real world photos of those assets. The drone goes back to the maintenance depot in which the pictures are uploaded here to the system. And then we apply this machine learning model that classifies those images and tries to find patterns, visual patterns in those images, which might indicate a higher need of maintenance in certain transmission towers. So once you have modeled all those things, this is an example here of the picture that you can see. In this particular case, it has identified 2 failures, but it doesn't end there, right? You can program a series of tasks here, which are related to that inspection program. So let's pick one task here. This task has processed 66 images. These are some of the metadata associated with this task. If I click on this task, I can see all the 66 images that were processed. And here I can do a drill down and see, for example, that this particular image that the drone took, right? It has this particular failure that was found by the machine learning model. Again, all associated with the digital twin that represents that tower, right? This is the defect that was found in this particular picture. You can also scroll here and see other angles, other pictures that the drone took, right? And all this is integrated into this workflow, right? So what is the goal of an application like this, right? As we mentioned, this has the digital twin capabilities as the backbone. But again, the outcome that the digital twin, that hierarchy is producing is an inspection result in which you can see, for example, all the drone pictures that were taken in a particular inspection program, the exact location that the picture was taken from, the defects that were found in those pictures. And then from here, you can generate, for example, a CSV report or some other type of report that would then guide these maintenance personnel to the areas that require maintenance, and you can also program. You can also schedule the entire maintenance program based on this optimized workflow. Right. So the last thing I want to show is a little bit under the covers. So we talked about 2 types of machine learning models that are associated with our digital twins. I just wanted to show a little bit of the capabilities there under the cover. So these are the 2 models that we talked about. In the first example, the digital twin was using this anomaly detection prediction model. In the second example, we were using this image-based image classification model. But in either case, I think what matters here is that you have the ability to manage here in Lumada one or more machine learning models. This is a component that's highly scalable. So if I click here, I can see the type of model that has been applied. I can see what is the endpoint. And if you're in machine learning model, you know that one of the features that is always required is that you have to train the data set. You have to train the model with a particular data set. So here you can see all the data sets. This is an S3 bucket where the pictures from the drone were taken. And these are the pictures that we use to train the model with. The other thing that you can see is, for example, in this model, I can click here and I can visualize all the versions of that model. In this particular case, there's only 2 versions. If you're in machine learning, you know that models can drift. Models may require retraining over time because conditions in the field change and things like that. So here we have a comprehensive infrastructure to manage all the versions that a data scientist or an application person may want to control. So here you can see all the parameters that are associated with these versions. You can see which is the version that's currently deployed. Right now it's version 1, but we can see that in this case, there's another version here, which is already trained. So at any point in time, when this is ready, if this is demonstrated to be a model that's better than version 1, I can very easily come here and just deploy the newer version, and this will then automatically take over from version number 1, right? The other thing I can do, I can select one or more models here, versions here, and I can compare the metrics and statistics. So then I can see which is the version, right, that's more suitable for the conditions that I want right now, right? So these are some of the under the covers that power applications like this one, right, that to really automate workflows, that really enable, right, workers to be more effective and more efficient out there. So with that, I would like to hand it over to Steve to cover some customer examples.
Great, thank you, Fabio. Thank you for that great presentation. Wanted to talk a little bit about a couple of customers we're working with and have worked with regard to industrial data ops as it applies to creating analytic solutions and also data management solutions for them. One of them is a global theme park provider where we worked very closely with them for quite a few years now. The projects we started with were really more around visualization and notification for maintenance personnel to be able to take action on different pieces of equipment breaking down, for example. But they wanted to be more proactive and also to augment their staff so that the people that they have in their organization that are coming in get a little bit more runway in what to do when maintenance activities need to be done. So a little more forward warning as part of what would happen. So as Fabio talked about, we basically employed a digital twin capability that would not only create up a data model of the different assets that they had with all the different sensors and reactions that would happen as part of that, but also to interface a third-party simulation package that provided a first principles physics-based model that could create synthetic data. And that synthetic data would provide a better ability to train the model to be much more accurate in predicting failure. In fact, we were able to tune it for a 48-hour lead time to be able to notify them of a problem from a maintenance point of view so they could take action more efficiently and then reduce the amount of effort and also improve the uptime for the different pieces of equipment inside of their theme park environment as part of that. So much better customer experience resulting as part of this project. So that's an example of asset maintenance and predictability around that. On the next slide, I also wanted to talk a little bit about the other side of the coin, which is really around data management and what's required for an industrial organization. As you know, these utilities, for example, are constantly under stress to provide better customer service capability for the people that they serve. And as part of that, they've automated much of their process at the field level But what has really been needed is to provide better visibility to more people in the organization, like customer service agents, for example, or people who are making decisions for long-term planning for a utility, and be able to integrate more data to be able to do that. What we were able to do is pull together a full solution from a data integration and a data management point of view and analytics to provide a 360-degree view of the overall operation. So this is including smart grid information that would be merged with customer data, weather data, grid status, partner information, demand, and so forth, all integrated together into a single view for operations people to use. So now that when somebody calls up with a problem with their particular service, they can more quickly troubleshoot what might be going on, see everything that's going on around the situation, and take action on that, providing a greater situational awareness for all their employees to take action as part of that. So another ability, if these, once again, if these companies aren't continually improving and optimizing their processes, they're falling behind today. So this ability provides that additional capability to really optimize operations across the entire business. Thank you very much. If we can move now to the next slide, and want to thank everybody for your attendance today, but we'd also like to answer some questions that have come in here. So maybe back to you, Dan.
Great, thank you. Thank you, Steve. And thank you all for the excellent presentations. You know, and especially with the demonstration and the real world use cases, I think it really brings to focus the value a digital twin provides. And one of the key points I wanted to reiterate that you heard both Steve and Fabio stating is that the digital twin is the backbone of the systems. It brings out one of the fundamental foundational points also included in the digital twin consortium definition is that the synchronization of the data is needed to ensure the fidelity, the accuracy, and the precision is maintained between the digital twin and the real world entity and process. So again, great presentations, great examples. So let's jump right into the Q&A. We've got about 10 minutes left here. So we'll start with Matt. What are the market trends that you see driving the industrial AI adoption, and who are the main AI software providers?
Thank you. That's great questions. So what we see in industrial AI is that there's a lot of partnerships, obviously, with hyperscalers, with other traditional vendors. There's also quite some changes in the market. By that, I mean that before you used to decide between making or buying your traditional solution. Now you can just go ahead and partner with a vendor. So this dichotomy is quite fading. In terms of vendors, if we split between hardware, traditional vendor and services, we have people like SAP or Samsung for hardwares, SAP making the software, and we have also a lot of consulting companies like Capgemini, Deloitte, or Accenture helping you throughout this journey. But also we have Hitachi helping you with AI solutions.
Mm-hmm. Excellent. All right, well, thank you. One of the questions also came out is, who do you see as, or what do you see as the best practice in terms of building an analytics group? Is it a center of excellence with domain experts or departmental groups? Maybe you could comment on that, what you've seen based on your analysis.
Thank you. From the feedback I got when interviewing end users or vendors, I think it's quite a central decision to be taken. So at the high level, CEO level, kind of executive decision, but also, yes, it's important to have a decentralized view and kind of so leaders in every of the teams that are involved. Excellent,
thank you. Maybe this goes to Steve. AI needs a human touch. So how do you see that being scaled?
Yeah, so there's different ways that you can do that. Of course, you know, from a scalability point of view, there's a limited number of people and trained employees that people have that are building analytics. And you know, we do a lot of business with people in the IT organizations and the engineering organizations that are responsible for organizing data, building analytic models, deploying those models as applications. So there's a whole pipeline of activities that happen as part of that. You can leverage tools, for example, like we make, to be able to make the effort that those people need to apply to making analytics less burdensome for them. So that includes the ability of a data catalog where you can easily pull together data and organize it inside of your data lake, turn your data swamp into more of an organized lake capability to be leveraged by many different individuals. That includes governing that data. If there's sensitive data that you want to manage and leverage with a partner, for example, like an equipment vendor, to give them specific information, you can manage it that way. You can organize data sets that have been certified by subject matter experts. So, the analytics people who are developing it can feel confident that the data is trusted. Then you can also set up a little bit easier process for data pipelining. So, data coming from different sources, both OT and IT based, to convert that in an organized way, to transform it, clean it as it comes along, validate that it's falling in the right levels of units and ranges that you would expect to see, and then also to give context to it across multiple sites. So you may have a temperature sensor that is named one thing at one site and named a different thing at another site. You can rationalize that so everybody understands that those two values are now temperature sensors that are being be leveraged for a particular purpose. And then finally, of course, we also provide services. So we have a large services organization that can be applied to help augment your staff if you want to go that route. Really different ways that can be applied to optimize your existing staff for analytic development.
Okay, great. I guess along those same lines, referring to the use cases that were presented, what level of internal resources do you see are required from sustaining these AI models? As Fabio was pointing out, you need to be continually updating these based on the information. What skills do you also see applied in that case?
Fabio, you want to address this?
Sure. Yep. Maybe I can take this one. So it varies depending on what is the skill set that a particular customer has in-house. Some of our customers, they have full-blown data scientists with PhDs, tens of those in-house, and they're happy to work with systems which are code-based, like Jupyter and others. And we have the tools that integrate into all this infrastructure that allow data scientists to do that. But we also have other customers who are less interested in the tinkering process, right, with the models themselves. And they are, for example, data analysts or other types of audiences which are not data scientists. We also have the tooling which allows you to do low code or no code model retraining. And those allow, for example, these applications that I just showed, like the image-based inspection or like the anomaly detection prediction, to be maintained by a different audience, if you will.
Mm-hmm. I guess there's a couple of questions around that in that context. If we look at the process testing, is it possible to have the results read directly into the process control? Currently the results are read, documented, truncated, reported. At that point, the data is interpreted and adjustments can be needed, but can you read those directly into that process control?
Right. So I think we touched on how we do the read part, which is using that first component that I demonstrated. But it's also one of the intrinsic notions for us in the digital twin that you can also send commands back, right? Obviously, if you're in the industry, you have to be very careful as to what things you're sending to the field, originated from the digital twin. But some use cases where the risk and the ramification of that action is well understood and, let's say, deemed safe, it's also possible that, for example, the result of a simulation, the result of an optimization that was done at digital twin can be sent back to the industrial device itself using the same protocol that we read from. Or in other cases, we may use a slightly different route in case there has to be, for example, a management of change process applied to it. We can also integrate some of those systems to allow the full end-to-end process to be supported for our customers.
Mm-hmm. I think both yourself, Steve, and Fabio were talking about the risk and the security of that data. One of the questions came out is are you seeing, and is it possible where you would have blockchain interacting in this point of view? It
is possible. I think the blockchain question is still very nascent in the industry, especially in industries which are more conservative and slower to adopt certain things. But as you need, for example, a public ledger or to guarantee, right, that the transaction cannot be undone. I think in some of those applications, it is possible to integrate those, but those are still use cases which are mostly in development for the majority of our customers.
Mm-hmm. So early stages really, but you are seeing some areas where they are being adopted and looking at how they can apply it.
Mm-hmm.
Great. I think that also brings up another line of view is where the connectivity about the equipment and the offline connected data, like work orders and log files, all of those types of things. Those are also, you're seeing those also being ingested by the digital twin as well, correct?
Absolutely. I think it's all part and parcel of the Notion digital twin that we want to support, which, as we mentioned, supports not only, right, the real-time data originated from the PLCs, from the sensors, from the OT devices, but also things which live in photos, right? Like we just demonstrated here in the inspection application. You could have logs which are scattered across different systems. We have data collectors which can read from those systems and bring that to the same analysis and machine learning model capabilities that we demonstrated here. You may also deal, for example, with design documents which may exist only in paper format. They have to be scanned and digitized. You may have maintenance work orders which perhaps exist only in a piece of paper. So all those things can and should be integrated into digital twin to provide that holistic access to the data, not only to the real-time data, but also to the these other types of related information, which is part of the broader outcome, right? If you're talking about a maintenance outcome or a scheduling outcome, some of those things may exist in different types of data sets. And as part of the Lumada platform, we have the connectors to integrate all those kinds of data sets as well.
Great. I think let's pass this back to Matt. One of the questions is around the most common AI use cases in the manufacturing industry that you're seeing. Are predictive maintenance and predictive quality control the most common for AI, or are you seeing other areas?
Yes, exactly. So from what we've seen during research on industrial AI, predictive maintenance and quality inspection, for example, with those robot dogs or with drones, as we've seen during the demonstration, as well as manufacturing process optimization. By that, I mean any kind of paper-based process that is not digital can be improved with AI, and that is a big use case.
Mm-hmm. Excellent. I guess along those lines, and this is since we're coming to top of the hour here, maybe this question goes to all of you, is could you summarize the top 3 things essential for ensuring success in applying AI and ML? So maybe we'll start with, well, it looks like you're thinking about that one, Matt. Maybe we'll start with Steve.
Sure.
What would you say?
So some of the things I've heard is, always when you're starting off, you should start with what are your top use cases that you want to do, because you want to build momentum. And what are the things you should be focusing on as an organization? Is it quality? Is it cost savings? Is it dealing with maintenance problems you're having? Availability of equipment, cost problems? Is it supply chain related? What specifically are some of the pains that you want to approach? And start off with build enough of the data management and the analytic capability to serve that use case. But as you do it, make sure that you're not pigeonholing yourself into just doing that particular solution. Make it and do it in a platform environment with the idea of scalability from the beginning, so you can actually spread out from there as part of that. That's one of the main things I've heard.
Mm-hmm. And I think that follows also very closely in terms of, as you brought out initially, with the capabilities. It comes back to, and this is one of the sayings our co-chairs, one of our co-chairs has, is what job are you hiring the digital twin for? Mm-hmm. And look at it in terms of those capabilities first, and then look at the optimal technologies to accomplish that. And I think, Fabio, you brought out a great point too, as well as the being able to enrich these models with this data that's coming, that's being provided through this real-time updates from digital twin, the actual information, the actual data that's being acquired in real time, now being able to enrich those models. So I think that's a great point. One of the questions came back. I just wanted to capture this one because that's essential here is, can we just apply ML models, ML and AI models, and provide customers predictions and diagnostics of faults without building digital twins? I think that misses out on the opportunities, and I'd like to hear your thoughts on that as well, that a digital twin can provide in terms of the value.
I guess the answer is yes. If all that you want to do is to just do, let's say, ad hoc AI and ML, you can always, let's say, go and start tinkering, right, in Jupyter or whatever tool you choose to do that. But once you start thinking about scaling, having, right, a maintenance, right, a sustainability plan for this, having a life cycle for a solution like this, deploying thousands of these things at scale, and having really a comprehensive governance model for these things going forward, which is what some of our customers really value. I think if you're just doing things ad hoc without having a backbone to kind of serve the foundation, there may be challenges down the road.
Yeah, agreed. And I think that's a great point, is really at scale when you look at these and being applied in those areas. So Matt, any comments?
Yes, coming back to your three most important topics, I think it's quite important to know where you're starting from. There's a lot of good tools out there to assess your digital maturity level within an enterprise or within a team. And also something that often comes up when we talk to end users is to keep track of what is really the use case you're focusing on and how much data you're creating, because almost every end user that has been using AI comes back to tell us, yes, we started with that, but we saw the amount of data that we created, and now we have so much more use cases, and it's spreading out so fast. We're really getting more data than and more value than what we expected, and I think that's very important.
No, that's a key point, and also stressing, you know, from the consortium, some of the areas, this capability toolkit, so that's available for download, and I think it highlights some of the key points that both Steve and Fabio you brought out, and then also it's really bringing out the fact that, you know, less is more. It's what's the signal for the noise, right? And how do you be able to understand that? And I think it's really been shown in many cases through here. Again, great use cases, great examples of this, great discussion. So I just want to say we're ready to wrap it up here, but thank you all, gentlemen, for taking the time out. And again, Lucian, thank you for bringing this all together.
Thank you all. This concludes the program for today. We do have a number of upcoming events, so feel free to take a look at our events on our website. Thank you, Hitachi Ventura. Thank you, Dan, Steve, and Fabio for great insights. And everybody will be receiving the link with the recording within the next couple of days. This concludes the program for today.
Thank you. Have a good day.
Thank you very much.
Thank you. Have a good day.
Bye.